Good evening, students. So, in the last class, we saw the Hamilton principle, some examples for continuous system as well as for discrete system, 2 degree of freedom system. And the Hamilton principle is quite versatile, especially in the continuous system. We saw that even the boundary conditions automatically comes from the formulation. The Hamilton principle is even applicable for the non-conservative system. So that is called extended Hamilton principle. So we will now today will derive the Lagrange equation from Hamilton principle. And if time permits, we'll take some examples using the Lagrange's equation. So in Lagrange equation also, we need kinetic energy and potential energy and virtual work to obtain the equation of motion. So all these three principles, the principle of virtual work, Hamilton principle, and Lagrange's equation, they are used to obtain equation of motion of the system. These principles, they don't solve the equations. The solution of the equations will be taken up in the subsequent classes. But these principles give us the equation of motion of either continuous system or multi-degree of freedom system. So let us see the derivation of the Lagrange's equation from the Hamilton principle. So I hope now this is ready. Yeah. So today, initially, we'll derive the Lagrange's equation for holonomic system. So we have a dependent variable, that is Ri, which is nothing but the position of a particular particle. Ri is the position of the particle, and this position will depend upon the generalized coordinates. So generalized coordinates are q1, q2, q3, and for n degree of freedom system, we'll be having n generalized coordinates. Also, this position will depend upon time because we are dealing with the dynamic forces. So the position can be expressed as a function of n number of generalized coordinate and the time. And if we take the derivative of this with respect to time to get velocity, that can be written as dri by dt, and this total derivative can be expanded in terms of generalized coordinate. So delta by delta q1 dot. Similarly for q2 and qn. And then because it depends upon time also, so partial derivative with respect to ri of ri with time. So this is the expansion of this total derivative because this ri depends upon all these parameters. The first n parameter, the terms can be put in a summation form because they are similar in nature. But del I by dt can be put separately here. So this is the velocity. Actually, we are aiming to obtain the kinetic energy of the system. So we obtain the velocity. So as we know, the kinetic energy is given by half summation of all the particles for all the particles mass into velocity square. So the velocity expression which we obtain we'll substitute here. Only thing here, because there are two velocity, so two dummy variables we have used. One is the R and another is the S. Because dummy variable will not make any change because that many terms anyway we need to integrate. But when we multiply them in the summation form, we will get terms like this. So simple as we do the algebraic multiplication of two terms. So like that, if we do, we will get three terms out of this, and this will be the common terms which will be getting from if we multiply this with the uh, this with the this, that means and the second term with the first term. So, and because the dummy variable can be, because that is a summation from 1 to n, so s or n does not matter, so that will add up to give this, the two terms. And this is the last one is when we multiply the second term of the second term, the second bracket. So this is just a simple multiplication of this velocity terms to get the kinetic energy. As I mentioned, the RS are nothing but the dummy variables. Now, in general, the kinetic energy depends upon not only the displacement and also velocity and time. So, in general, so often we'll see that it will depend upon velocity and time, but in general, it can depend upon displacement also in some cases. So if we take the variation of the kinetic energy, so in that case, the variation of this displacement terms will be coming. So it's similar to the total derivative expression. So we'll be having n terms for the variation of the displacement and n terms for the variation of the velocity here. Time variation is not defined, so that term will not come in this particular expression. So actually, in the Hamilton principle, we know the variation of the kinetic energy and variation of the potential energy is there. And so we are trying to express these terms in similar lines. So here, if we integrate from T1 to T2, this variation of the kinetic energy, so is one of the terms in the Hamilton principle. So that part by part, we are trying to get the this kind of expression. So if we integrate this with respect to time from T1 to T2, we'll get this expression here. Even the integration and the summation order has been changed. So integration we have taken inside. So this is the first term and this is the second term of the velocity. Now, because as we have been doing, wherever there is a variation of the velocity term in of the generalized coordinate, we want to do the integration by part. So for that, I'm taking this particular term separately here, delta variation of velocity cube k, and that can be written in the form of derivative, and I'm interchanging the derivative and the variational operator order. I'm bringing in the variation so that when I do integration by part, this will go. So this term can be written like this. So this expression from the above manipulation will give the like this. So now in the next slide, I'll take the integration by part of this particular term. Only this term I'm taking. This will add up once we get the expression for this. So this is the same expression as the previous one. Now I'm doing the integration by part. So this is the first part as it is. Then the integration of the second part, this derivative will go. So only variation of the displacement will be left out. and T1 to T2 is the limits minus integration T1 to T2 derivative of the first term. So this is the time derivative of the first term and the integration of the second. And we know that this variation is not defined at T1 and T2 because they are 0 at T1 and T2. So the first term will be 0. So we're left with only the second term like this. So now we have obtained integration by part of the second term of the previous expression. This we'll substitute here, and now because this also contains delta Q variation, so they can be combined also in this form. So this is the first term as it is. Second term after integration by part, we got this, and now we combine this because delta QR is common here. So I'll take common here within the integral. So this is this term, and this term is coming here. Negative sign is taken out, so this the variation of the kinetic energy is now in the required form, where only the variation of the generalized coordinate is there. Now we'll see the force, external force. So if, let us say P number of forces are acting on the system. Okay, we have generalized coordinate n number, but let us say we have P number of forces acting. This is the actual forces acting on the system. So the virtual work because of these forces will be force into variation of that position where the forces are acting, and the direction of the dot product will ensure that displacement component is there along the direction of the force, so that we'll get the virtual work from the force. This variation of the position vector, as we have seen that Ri depends upon the generalized coordinate. So this variation can be expressed in their just like you take total derivative terms, because Ri is function of Q1, Q2, Qn. So we can able to expand like this. Here it depends upon the time also, but variation of the time we are not taking, so that term is not coming here. So this thing will substitute here, so that the virtual work expression Fi also I have taken inside the bracket. So after substituting the variation of the R in the generalized coordinate, I got these terms. So this summation is from J to P. P is the number of forces, external forces. Now, but here how many terms are there inside the bracket? Because we have generalized coordinate n in number. So this can be written as summation of n terms. So that you can see summation of n term. Order has been changed here, because summation order also we can able to change without any difficulty. So this is corresponding to summation of all this term. So K. So you can see this is the same expression as this. Now the two summations have come. One is the K is equal to 1 to n, number of generalized coordinate, and another is J is equal to 1 to P, which are number of forces. So this is the virtual work expression. So this expression for the virtual work is based on the external force, actual external force on the system. So now I want to introduce a new force. This is a hypothetical force, generalized force, QK. So this generalized force is similar to the generalized coordinate, in the sense that these forces are acting along the direction of the generalized coordinate, and they are n in number. Actual forces are p number, but these are the hypothetical force we are assuming or we are defining that let us say there are generalized forces which are acting at all the coordinates, and number of generalized coordinate is n. So qk is n in number, and the direction is along the direction of the variation of the displacement which we are giving. So if this is the case, then the virtual work because of this generalized force will be the force into the variation of the generalized coordinate. So this is the generalized force and corresponding generalized displacement. So we have n in number such generalized coordinate, and we are assuming that that many number of generalized forces will be there. So this is those terms. So if we sum them up, because they are n in number, so they can be written like this. So we have two expressions for the virtual work. One is from the generalized forces, another from the actual forces. So if we compare these two expressions, we will see that the qk, the generalized force, can be obtained in terms of the actual force like this. We compare this, delta q is common. Here summation 1 to k, 1 to n is there, so that is common. So this summation from j is equal to 1 to p will come here, and this term. So now we could be able to relate how the generalized force will be related with the actual forces, which are p in number, but generalized forces are n in number. So k is from 1 to n. So yes, so once we have the force in the system, in this equation can be used to obtain the generalized coordinate. So this is very important expression. Now, this is the Hamilton principle. We obtained the variation of the kinetic energy in the previous discussion, when the variation of the this virtual work. So if we substitute the variation of the kinetic energy, if you remember, these two terms were there, and for virtual work, this into delta qk was there, the previous one. So this one, and if we go back, the variation of the kinetic energy, this one. So this two expression we have put in the Hamilton principle. So you see, this is the Hamilton principle. We substituted that, so we got this expression in which outside the bracket we have variation of the generalized coordinate. Now again here these generalized coordinates are independent. They're independent, and also the variation of the generalized coordinate, as we have defined within the line T1 and T2, that is arbitrary. So we can able to assign any value to qk. So that means and this particular term is equal to 0. So Hamilton principle says the variation of this is equal to 0. So to satisfy that, the term within this bracket, square bracket, should be equal to 0, because this is equal to 0. So, and variation is arbitrary, so this cannot be 0. So to satisfy that, all the terms within this summation, there will be n terms. So all the terms should be independently equal to 0. So this is the expression for that, and where r can take from 1 to n value. So these are the n terms. So independently for all the generalized coordinate, this particular term within the bracket will be 0. And this expression is nothing but the Lagrange's equation of motion, in which we have the kinetic energy and the generalized force. QR is the generalized force, which we have obtained from the Hamilton principle. So basically, if we satisfy this condition, this will satisfy the Hamilton integration principle also. So now about this generalized force, we'll see more, because generalized force can be conservative and non-conservative. Two parts we can have. So this is the conservative generalized force, and this is non-conservative generalized force. And we know that for conservative forces or the conservative field, the work done is nothing but the negative of the potential energy. This we already obtained. The work done is equal to, in the conservative force field, is equal to negative of the potential energy. So the variation of this, which we obtained this expression earlier, if we take the variation of the potential energy also, which depends on all the generalized coordinate, so we will get variation of the potential energy like this. Here again, variation of the time is not taken, only the of the generalized coordinate is taken. So this is the coming from the conservative work done, and this is coming from the potential energy, because we know they are related, so we are equating them. Now if we compare the second term and the fourth term, we will see that the generalized force due to the conservative or the conservative field is nothing but the negative of the derivative of the potential energy with respect to the generalized coordinate, okay, where r can be 1 to n. So all the generalized force which are n in number is related with this. So if we know the potential energy, this conservative generalized force can be obtained from here. Still, we are not obtaining the non-conservative part, that will be obtaining separately. And at present, we'll retain this as it is. In the example, we'll see how the non-conservative force can be obtained. So now, in the going back to the Lagrange's equation, if we go back here, so this we split into two parts, conservative and non-conservative part, and the conservative gives an expression like this. So if we substitute that here, we will get this. So this is the non-conservative, this is conservative part, this is non-conservative part. First two terms as it is. Now this can be rearranged. We can bring this q terms in the right side, because generally the external force we keep in the right side in the equation of motion. Potential energy derivative with respect to qr is here. So this is another form of the Lagrange's equation, which is valid for the non-conservative system. But if we have the system which is non-conservative, then the right-hand side term will be 0. Non-conservative force will be 0. So let us see some more form of the generalized this Lagrange's equation. So generally we write the Lagrange's equation in terms of Lagrangian. Lagrangian is defined as kinetic energy minus potential energy. So the previous equation is same. This is the same as the previous slide expression. So I'm rearranging this. Generally, the potential energy will be independent of the velocities. Potential energy will not depend upon the velocity. It will depend upon only the generalized coordinates. So I have arranged here t minus v derivative with respect to velocity. So anyway, if I differentiate, the potential energy term will not contribute anything. So this will give same as this. These two terms are combined here. So t minus v. So this are combined minus, so this shape, non-conservative force is here. So I wanted to write in the Lagrangian form. So that's how I written here. Now I can replace t minus v with L. So this is the another form of the Lagrange's equation for conservative system. And for non-conservative system, as I told, the right-hand side term will be 0. So this is the conservative system Lagrange's equation. This is a special case in which there is no external force. So so if you see here, the first term is related with the Lagrangian derivative with respect to velocity, and then the time derivative of that minus is the Lagrange and derivative with respect to generalized coordinate. And they are n in number. So these equations are n in number. So if a system is having n degree of freedom system, we'll be having n generalized coordinate. So we expect that many equation of motion. So that's why here we have n number of equation of motions. So if you have any questions on this, I will stop here and then I'll take up the example. So if you have any question, please raise your hand. Any question on the derivation of the Lagrangian equation from Hamilton principle? Any step if it is not clear? Okay, so there is no question. So I'll go ahead with the example. I'll take few examples and first example is the same as we have done for the virtual work and the Hamilton principle, so that you can able to correlate uh, how we obtained earlier and now. So we already obtained the generalized coordinate for this in the previous example. We already obtained the kinetic energy using the during the Hamilton principle and the potential energy also. So the same kinetic energy and potential energy will be using here. Here the virtual work, that is a non-conservative part, non-conservative. Okay, so non-conservative part here we have the force. This is the force which is basically because the displacement is there. So this also I think we obtained earlier. So once we have the total displacement of the point where the force is acting, we can take the variation of that particular displacement. So that will give two components. One will be having variation of the x, and another will be variation of theta. So this is the force into the displacement of this particular point, which will be x plus this L sine theta, and that will give, if we take the variation, we will get this. And if you see, I have written like this. So x variation of small x, so and h variation of theta. So they will be actually non-conservative force when we are taking the first generalized coordinate. So in the previous here, they will take that particular values. So when we are writing the Lagrange's equation for x, then the small x, then the q nc will be x, and when we are writing the Lagrange's equation for theta, q and c will be h will be this term. So here the non-conservative force is derived here. So now we'll write the Lagrange's equation for two generalized coordinate. This is for the x. So we'll replace q1 with x or small x, and the right side q and c, which is non-conservative force, I'm writing as capital X because I have defined that here as capital X. Capital X is nothing but F. Similarly, the generalized coordinate when we have theta, the right side is h, which will be the previous expression. So we have two Lagrange's equation. One is in terms of generalized coordinate q1 is equal to x, another is that is q2 is equal to theta. Now, because L is defined as T minus V, kinetic energy minus potential energy, so now we need the various terms to be differentiated. So like del V by del X dot. So del L by del X dot if we differentiate this with respect to x dot, you can see that the first term will give this, second term is having x dot, so that will give this, third term is having no x dot, so this will be 0. In potential energy anyway there is no x dot, so this will not contribute anything. So the derivative of L with respect to x dot is this simple derivation or derivative we can do. Then in this second one, we have the very sure derivative of L with respect to theta dot. So if we do that, the first term will not contribute, second term will contribute because here theta dot is there. So that is here. And then third term also will contribute this. Potential energy will not contribute. So this can be rearranged like this. Now, yeah, this one, because here we have del L by del x. So if we differentiate this with respect to x, the first term kinetic energy will not contribute anything. Potential energy only here x is there, so that will be kx minus because t minus v, because v is in the minus one, so that's why this minus is coming. Similarly, here del L by del theta will give us the differentiation. So here this will not contribute, this will contribute because we have theta here. This will not contribute, this will also contribute because theta is there. So those two terms will give us the. Now we can substitute this in this. So you can see that del L by del x dot are substituted, and derivative still we need to perform. And this is also from question H we can put here. And x we have defined in the previous slide is f, and h is fl cos theta. So this is x, h is this one. I think this, okay, this is the same equation. So here I will perform now differentiation with respect to time also. So this becomes double dot. And here, because there are two terms, so two terms, when we differentiate, we'll get two terms from this. So this is the same equation, and this is a nonlinear equation. Then the second equation, this one, if we substitute, we will get this. Here h is there, fl cos theta. If we simplify this after differentiation, we will get a nonlinear equation. So these are the nonlinear equations. Again, because we will be dealing with the linear system, so for small angle theta, we can approximate sin theta is theta, cos theta is 1, and we will neglect the nonlinear terms which contain the multiple of the generalized coordinate x and theta multiplication. So those terms if we neglect, we get the two equation of motion. If we put in the matrix form, we'll get like this, and this equation is same as the previous examples we have been obtaining. Okay, so if you have any questions on this, you can ask. Otherwise, I will go for this other example. If you have Kiran.
Sir. Yes, sir. Sir, on the 65th page, equation number 2, first term I didn't go how it came.
Which slide? 50?
65th page, 65.
60?
So just 65, just the page before. Sir, in this equation 1, the first term, that is d dou L by dou theta dot.
This one. Which equation?
No, sir. Dou L by dou theta dot. First equation.
This one.
Just after that, dou L by dou theta dot.
This one.
Sir, below, sir.
Then you give the F, E, which
one,
equation?
I, equation I.
Equation I, no? That's why. So this one. Yeah. So this you are differentiating with respect to theta dot.
Yes, sir.
T minus V.
Yes.
So this is not contributing anything.
Yes.
This will contribute.
Yes, sir.
Theta dot will
Theta
go
dot.
on.
Yes,
Yeah.
sir.
Theta dot will, I think they should go. This will not be there. And is
Okay,
not
sir.
there here. So I think there is
Okay.
a, so that theta dot typo is there. Here is not there. This should not be there. Finally, it is not here. Yeah. The noise is okay.
Yes, sir. 1/2 will also go now, sir. 1/2 will. Yes, sir. Okay, 1/2 will be there.
No, 1/2 is here because this is not square.
Okay, okay.
Yeah, it's not square. Yeah.
Okay,
Any
thank you,
other?
sir.
Yeah. Any other question from anyone? Okay, so this example you have been seeing, so I think there's no much questions on that. So I'll take another question. Yeah. Yeah. So now here we have a vehicle model which is carrying some cylinder. So this is one of the mass we are considering. This is connected by some coupling. So stiffness of that is there. And this is a trolley having some mass M2 and is carrying some cylinder and is supported by some element which is having some flexibility. This can roll over this by some small angle theta. So generalized coordinate we are defining of this as x1 because they can move in the horizontal direction. So let us say the generalized coordinate is x1 of this. This trolley is x2. This can roll with the theta angle because the radius is r. So the distance traveled this will be r theta during the rolling. So I'm taking that as r theta direction, positive in this direction. So this is a 3D of freedom system in which x1, x2, and theta are the generalized coordinate. R is constant. R is constant, and the mass of this is m3. R is given, so we can able to obtain the polar moment of inertia of that separately, no problem. So generalized coordinate is 3, so we expect there will be 3 equation of motion for this. So first step will be to obtain the kinetic energy and the potential energy of the system. So kinetic energy will be for the mass m1 because this can have only the linear motion. So kinetic energy is simple, half m1 x1 dot square. Trolley also can have only linear motion. So half m2 x dot 2 square. So this is the second kinetic energy for the trolley. This roller is rolling over the trolley and trolley is moving. So the roller is having two motion. One is the rolling as well as the translational. So rolling motion is half IC3 theta dot square. So this is the polar mass moment of inertia of the cylinder. So this is the rotational part. But this is moving along with the cylinder, so along with this trolley. So we need to consider the translation motion of that. So this is that particular part. Not only because of the rolling is moving by r theta, but the trolley itself is moving by x2. So this will be the potential, the kinetic, this will be the displacement. If we differentiate, we are getting the velocity of the absolute velocity of this particular cylinder. So square of that will give the kinetic energy. So this is the main thing. M1 and M2 is having kinetic energy simple, but this cylinder is having the rotational part and the translational part. So we need to be careful in obtaining the kinetic energy. So once we know the kinetic energy, I think the other derivations will be simpler. So the potential energy. Potential energy can be there in the spring. So the spring is having relative displacement x2 minus x1. So, and this spring also will contribute to the potential energy. So the difference between these two will give us the extension of the spring. There's no other potential energy in this. So this is from the first spring, the difference between the two displacement of this two ends of the spring. And here, yeah, I think I got wrong. Here, because the spring is attached to the trolley, so the absolute extension of the spring will be just the r theta, because it's attached with the trolley. So the extension will be how much it is rolling, that much only it will extend. So r theta will be the extension of that, not the difference between these two. So r theta will be the extension of the second spring. But in the first spring, the difference will come because they are separate parts. But because this is mounted here itself, so and moving along with the trolley, so the extension of the spring will be just how much it is rolling. So once we have the potential energy and the kinetic energy, we can able to so here you can see there are three generalized coordinates. So this is one of the Lagrange's equation for x1, this is for x2, and this for theta. So these three equations will give us three equation of motion when we differentiate this kinetic energy and potential energy one by one. So here this will be simple mathematics. So if we are doing for this, you can see directly I put here kinetic energy. Anyway, potential energy is having no velocity term, so that will not contribute. And then this is for the potential energy. So this just potential energy. Okay. So this is another form of that in which directly kinetic energy and potential energy there instead of the Lagrangian. So directly we can substitute, and if we differentiate, we will get equation of motion like this from the first equation. Similarly, for the second equation x2, once we substitute the kinetic energy and potential energy, if we differentiate, we'll get the second equation of motion. Similarly, when we substitute in the third one, so this is simple differentiation, so we'll get the third equation of motion. Here all we are getting is linear equations. There's no nonlinear terms. So this can be simpler. So this is the third equation. So all three equations which we obtain for x1, x2, and theta are these. Now they can be combined in a matrix form. So here, because we have three generalized coordinate, so here in the inertia we will be having x1 double dot, x2 double dot, theta double dot. So this is the first equation. So you can see here only x1 double dot is there, theta double dot is not there, so remaining term is 0. Even x2 double dot is not there. So this is the first. So if you expand the first row, we'll get the first equation. Second row, second equation. Third row, third equation. So I generally prefer that in the assignments you should write the final equation of motion in the matrix form, so that it is, because here you can see that the property of the mass matrix is symmetric, stiffness matrix is symmetric. So this is one way of checking whether you are getting the correct mass matrix or not, because all the system we will be dealing with, generally there will be symmetric mass matrix and stiffness matrix. But here you will see that the mass matrix is coupled because this is an off diagonal term. Even the stiffness matrix is coupled. So both mass matrix and stiffness matrix having coupling. Here in the stiffness matrix, x1 and x2 is coupled, but in the mass matrix, x2 and theta is coupled. So basically, to solve this, we need to solve all the equations simultaneously. None of the equations are independent of each other. Okay, so here, because we have three generalized coordinates, so when we solve these equations in subsequent classes, we will get three natural frequency of the system. And here, when we are dealing with the multi-degree of freedom system, even we'll be bothered about the motion, how the various generalized coordinates are having relative motion with each other. So that is called mode shape. That will be seeing how we will be obtaining them. So that is also important, how the various masses are having relative motion with each other, and they will be associated with their natural frequency. So any question on this particular, if you have? This was simple example. Yeah, Akshat.
Sir, you said that x2 and theta are coupled. What is the meaning of that?
Yeah. When I'm saying x2 and theta are coupled in the mass matrix, so that means if you see here, x2 and theta are there in the equation of motion here also. Okay, so they are coupled. That means they have here x2 is there, theta double dot is also there. Okay, I think this should be x1. And here, like here, theta double dot is not there. Okay, so this is generally coupling means they are interfering the motion of each other. Okay.
And sir, this mass matrix and stiffness matrix are always symmetric, or for this case only?
No, always we'll find for our system always it will be symmetric. In some special cases they are not symmetric, but most of the cases which we'll be dealing with, they will be symmetric, and is having meaning to it because once they are symmetric, the natural frequency which will be getting, or whatever the roots will be getting, will be real. When we find the eigenvalue of this equations, the roots will be real. So if they are not symmetric, then we may get complex eigenvalues. Okay.
So, for both discrete as well as continuous system.
Yes, yes. Anyway, continuous system, that is an infinite degree of freedom system. So we'll not be putting in a matrix form to them.
Okay.
There will be partial differential equations. Okay.
Okay.
But continuous system, because continuous systems are very difficult to solve for complex boundary conditions. So we will able to get the solution for very simple cases only using the partial differential equation. So generally those continuous systems are approximated to some discrete number of degree of freedom. Okay, so that as we'll progress in the subject, you'll understand that because once the continuous system is having infinite degree of freedom, it will be having infinite number of natural frequencies. But all natural frequencies are not of practical importance. Okay, so only the few lower ones are important. So the continuous system will discretize into a discrete system having some n degree of freedom. Okay, and then there, whatever the matrices will get, often they will be symmetric. In some cases, they may be asymmetric. So that is, I think, maybe we are talking about chapter 5 or 6. Okay. So we are in the chapter 2 at present. Okay, so I have one more I think I can finish this so that I can start a new chapter in the next class. So this is one more example. This is a string which is fixed at two ends. In between the string, there are two masses, M1, M, and 2M. So there are two masses. So this string is disturbed transversely. So in the arrow shown, if we disturb it, so is having we are trying to study the vibration in the transverse direction of this and this. So the string generally, like in a guitar, okay. So generally we give some tension to it. So is having some tension. The initial tension is T naught, and because of the initial tension, is having stiffness in the transverse direction. If string is loose, will not be having stiffness in the transverse direction. It may not vibrate. But if it is having stiffness, if it is having some tension, then only if you disturb it will vibrate in the transverse vibration. So it's having some initial tension, and we want to know what is the natural frequency of the system. So for that we need the governing equation or equation of motion. So here the stiffening effect is coming from the initial tension. Unlike in the spring case and other things, okay, the elasticity is there. So here it's coming because of the initial tension. Now, when these masses are disturbed, so let us say the first mass is having x1 displacement, second is having x2 displacement. Various lengths are symmetrically placed, so L by 3, L by 3, L by 3. Only two coordinates are required to define this. So generalized coordinates are x1 and x2 only. Theta 1 is not a generalized coordinate because there are two masses, so 2 degree of freedom we are considering because it's having only one direction motion. So now we want to obtain what is the potential energy in the mass when is getting disturbed by x1 this much. Okay. So because this string we are assuming is having some constant torque or tension. Even during deflection, we are assuming that there is no change in the tension. The tension in the string remains the same. So here when is getting displacement x1, what will be the tension in the string? That is same T naught. But what is the component of that along the x direction? Component of that will be x direction will be T naught sine theta. And sine theta 1 is x1, and so sine theta can be approximated as a x1 by L3. Actually, this should be tan theta. T naught tan theta 1 is approximated as x1 by L by 3. Because for small angle, sine theta and cos tan theta are equal. So this is the component of the tension around the displacement direction. So this is the force which is acting when this is getting displacement in the x direction. So the force into the displacement x will give the potential energy stored in the string when the first part of the string when we are having x1 displacement. So hope this is clear. The potential energy I'm obtaining the component of the force along the displacement direction of the string x1, and then I'm multiplying by the displacement, and half is giving us the potential energy stored in the first part of the string. So once we have this concept clear, we can obtain the potential energy stored here and potential stored here. So let us see. So this is we already derived in the previous left for the left string. This is for the middle string because here we have displacement at either end of the string x2 and x1. So the difference between these two is the extension that will be the relative displacement of the string. So here, that is the relative displacement. So this is the force component around the that relative displacement. Into relative displacement will give us the potential energy in the middle string. Similarly, the right string is similar to the left one. Only thing will be x2 here will come. The middle is having some change because of the two ends are having different displacement. So this is the change. So now this can be simplified and this can be expanded, rearranged, and we can able to simplify like this. This is the potential energy. Kinetic energy of the system is simple. First mass is having x1 displacement, so the velocity is square. Second mass, velocity is square. So potential energy is having no issue. Because we have 2 degree of freedom system, so we can write the Lagrange's equation for first and second, and then we can substitute this potential energy and kinetic energy in this expression to get the equation of motion in x1 direction, xy direction. And both are linear equation. They can be arranged in a matrix form like this. So here also you can see this is a mass matrix, this is stiffness matrix, which is symmetric. Mass matrix is uncoupled because off diagonal terms are 0. So you can see the T naught is contributing in the stiffness term here in this string. So this is the last example I was showing for the Lagrange equation. So if you have any questions on that, you can ask. Okay. So with this, I think we have finished the virtual work principle and Hamilton principle and the Lagrange's equation. So whatever the 3 problems I have given in the assignment 2, I think now you can able to solve them using this. And now you have enough time because the submission time is on 20th and then you have quiz on 30. So I think you can able to prepare the first 2 chapters, whatever I have covered. And in that, related to that, I will be asking the objective type questions. Okay. So I think if there is no questions, I can. Regarding the assignment, I think once we are submitting it, those files are there. I checked it, but I think you are not able to see them. Only when I grade them, then I think you can able to see them. So there is no issue if you are submitted. If you want to resubmit or change it, tell me. I will return that to you, and then you can able to resubmit. If you want to have some corrections in your assignment, just email me. I will return the assignment to you. Then you can able to edit that. Otherwise, if you have submitted correctly, no issue. That is there with all the files I checked today. Okay, then I'm stopping. So bye for now.